Welcome everyone to lesson 4 of Precalculus, which is called Polynomial Functions and Rates of Change. So let's get started. So I've got a lot of vocab for us today. First one up is a monomial. A monomial is a function that can be written in the form of f of x equals a times x to the power of n, where a is a non-zero real number, because if it was 0, it'd just be 0, and n is a real number. Remembering that mono is equal to 1. Polynomials are the sum of individual monomial functions kind of all stringed together. So a monomial can be a polynomial, but the polynomial has a little bit of a restriction on it, where the exponent for a monomial can be any number, any real number. For polynomials, they have to be integers. What makes integers a little bit different is integers are whole numbers. And more than just being integers, they have to be non-negative. So they have to be 2, 3, 5, 873. It doesn't matter as long as they are positive, non-negative integers. 0 technically would work. It would just make that term 0, the polynomial 0, and 0 is technically a polynomial. All right, so of a polynomial, remember it's written in this form here. The monomial term with the largest exponent is called the leading term. We call it the leading term because if it's in standard form, you would write that one first. It would take the lead. But sometimes mathematicians like to write things that aren't necessarily in standard form just to test themselves. So you're looking for the monomial term with the largest exponent, and that entire term, that a times x to the n power, is the leading term. The degree of a polynomial is that largest exponent. Whatever that largest exponent is, that is the degree of your polynomial. You'll see me use the abbreviation like DEG quite a bit. And the leading coefficient is the coefficient or the number in front of the x that has the largest power. All right, so let's do a little bit of practice with that and identify some parts of functions. So here in question 1, we have g and f of x. So what I'm going to do is look at the powers, and I'm going to put a box around the one with the largest power. It looks to be this one here. So its degree is its largest exponent, which is 5, and its leading coefficient is the number in front of the x, which is 3. F of x is written in non-standard form. It's not written in descending powers, so we have to be careful. Its leading term is right here, so its degree is 6, and its leading coefficient would be -2. You do want to include the negative if there's a minus sign or a negative in front, because we'll use this information to extrapolate about the function's behavior later on, which is why we have to talk about all of these definitions. So, speaking of definitions, here are some more vocab terms for you. So I'll try to put them all on the screen so you can pause the video if you need to, but I'm going to go through them quickly. We have a term called extrema, which is also called critical points in calculus, but extrema is just your maxes and your mins. And it's inclusive for all of them. So extrema is just a one-word way of saying maxes and mins. Local or relative maxes and mins mean if we focus on that singular part, it's the largest value or the smallest value in that interval. If we have a function and it goes from going up, increasing, to going down, decreasing, it would be a maximum. If it goes from going down or decreasing to going up or increasing, it would be a minimum. Now I'm going to use, when we talk about intervals, this inclusive and non-inclusive language. Inclusive just means that it is included. So if you're used to inequalities, x is greater than or equal to 3, we would say we want all values greater than 3, including the 3. Where if we have x is greater than 3, we want all the values greater than 3, but we're not including 3. It's non-inclusive. So inclusive you can think or equal to, non-inclusive you can think just not equal to. So when we talk about intervals, and we use interval notation a lot in precalculus and calculus, we use brackets to signify if we include that end value, if it's inclusive. We use parentheses for non-inclusive. So for example here, if we have parenthesis 3 comma 5 bracket, it means that we want everything from 3 to 5, including the 5, or 3 is less than x, which is less than or equal to 5. It's just a quicker way and sometimes a nicer way of describing a range of numbers. All right, so we want to find all of the relative extrema for this function here. Now do note, this is important, the function ends. It clearly ends here and here, which means it doesn't go towards infinity. So the easy one to figure out is this point right here is a maximum. So we would say there is a max at a max, we're going to say, well, let's say there's a max of the value, which would be 1, 2, 3, max of 3 at x equals 0. And if the function went off to infinity, that's where we would leave it. But for this function here, because it has endpoints, we do include the endpoints because they are hollow, they're not, or because they're solid, they're not hollow or just holes. We're going to include them. So if they are the lowest thing in their area, if I would zoom in, it would be the lowest value or the highest value, we would include them. Lowest meaning minimum, highest would be a maximum. So in this case, we have two minimums. So we're going to say we have a minimum of 2 at x equals -1, and we have a minimum of -1 at x equals 2. So when we describe maxes and mins, and we describe extrema, we want to, one, include the value. So we're saying there's a max value, there's a min value of something. That's the y value, that's the dependent value. And we want to describe the location. The location is its x, or its independent value. And all of these are relative. So it would be more precise for me to put relative max. Relative min, so on and so forth. Why? Because we do have something called a global or absolute extrema. So absolute extrema is when something is the absolute largest. It never goes higher or never goes lower than this value. If we look at this function back up here, we would say its absolute maximum would be 3, and its absolute minimum would be -1. Because 2 is a relative min, we can still go below it in some areas, so that wouldn't be the absolute min, but in its general location, it is the lowest. So I will leave this here for a second if you need to pause it and write that stuff down. Otherwise, we're going to move on. Do remember, and this is a very important note for us, absolute extrema is considered relative or local extrema as well. So even if it's the highest thing that it's ever going to be in that general area, it would also be the highest thing as well. So when you are asked to list both, like we're going to in this next question, wherever it says to list the relative extrema, make sure you include the absolutes as well. So we have this function here, and it's important to note, it's hard to tell from the diagram, that there is a closed dot there, and this end goes towards infinity. So absolute mins, it is the absolute lowest value possible would be at 1, 2, 3, 4, 5, so all these is y1. So the lowest value could possibly be would be -2, and that happens at -6. Maximum, because the function goes towards infinity, any number you put down that would be the absolute maximum value, I can pick something slightly higher, and then mine would win out. So because that happens, we're going to say that there is no absolute max. We're not going to say it's infinity, because infinity being a number doesn't necessarily make sense. So we're just going to say it doesn't have any absolute max or absolute mins. No, absolute maxes, my bad. Relative minimums. So if we look here, the function is a minimum here, here, and then our absolute min that we had before. Because it only wants the x values, we're just going to list where those x values of those points are. So we had the -6 from before, we have this negative 1, 2, 3, and this positive 1, 2. So we have 3 relative minimums. Maxes happen here and here. So we only have 2 of those, and those happen at, looks like, negative 4 and then positive 1. So if this was a test question, and you did not include the negative 6, you would lose a point on that, simply because anytime you say that something is an absolute min or max, it should also be included in the relative lists. Now, something I do want to note that isn't necessarily on here is if you have an open hole as an endpoint, like if this point here, instead of being a closed hole, was open, we would say it does not have an absolute minimum either, because you can get as close as that as you want, and I can find something a little bit closer. But that's more of a calculus concept, so for now we're not going to mention that much more, but do keep in mind that there are some weird cases that might come up in the future. So let's talk about something a little bit weird, and that is if we have a continuous non-constant function, meaning that the function is not a horizontal line, but it's continuous. We can draw the entire thing without picking up our pencil, and there are 2 values that are equal, then at least one extrema has to be between those. So I have some examples here. If we have this value and this value being equal, in the blue, there's 1. In the red, there would be 3, but there's at least 1. Because otherwise, if I were to draw this, and let's say we had a point here and a point here, the only way for me to connect those points is if I come back down, if I'm coming up, or if I'm coming down here, I have to come back up to hit it. Otherwise, I could draw a horizontal line, but then we're messing up the condition of our big idea here, which is that it has to be non-constant. So as long as we have 2 equal values somewhere in the function, there has to be a relative maximum in between them. Again, as long as it's continuous. And polynomials are continuous, so if they ever give you the fact that something is a polynomial, do keep in mind that that is enough for you to say the function's continuous. Speaking of the devil, let f be a polynomial function, so they're already telling us that it's a non-constant continuous function. So we have some values here. Let's write them as points. That might help us out a little bit. We have -2, 0. We have 0, 5. We have 4, 0. And we have 7, -1. So do we have any of the same values? This is y values occurring anytime between these. And we do. We have a 0 here and a 0 here, which we can see on the right-hand side of our points. So there has to be a guaranteed extrema between those. So we're going to say yes, because we're answering the question, are there any? Yes, there is a guaranteed extrema between -2 and 4 because they have the same value. Again, it's always good to explain yourself. So yes, there is something, and here's why. Last big idea we're going to have for today is if we have a polynomial function of an even degree, then there must be an absolute extrema. Even degree means that its highest exponent is 2, 4, 6, 8, so on and so forth. As long as the highest exponent is an even number, then we're always going to have either an absolute min or an absolute max. And how we determine whether we have an absolute min or absolute max is we look at the leading coefficient. If the leading coefficient is positive, then we're going to have an absolute min somewhere. And if the leading coefficient is negative, we're going to have an absolute max somewhere. We don't necessarily know where it is, but look at the question. Sometimes it's not asking what is it, just is there one? Speaking of which, I guess I lied about it being the last major idea. Do these have any absolute extrema? If so, which type? So look at the first one. This is our leading term. It has a degree of 4, which is even. So yes, it does have one. But which one is it? We don't necessarily know that one unless we look at the leading coefficient, which is positive, which means it's going up. So yes, f of x has an absolute minimum. All right, so if you haven't already, I want you to pause the video and I want you to try the other two out and compare what you get with me. And here I'm going to go. The leading term for this one is negative x to the power of 6, so the degree is even, and the leading coefficient is negative. So yes, we have one, and f of x has an absolute max. The last one, here's our leading term. The degree is 3, so I don't even need to look at anything else. No, because degree is odd. Very nice. Our last big idea of the day is about points of inflection with polynomials. So we've talked about points of inflection before. It's where the concavity changes from being concave up to concave down, or concave down to concave up. For polynomials, to identify how many points of inflection one has, it's going to have at most n minus 2. So a degree 3 polynomial is the first polynomial that has the possibility of having a point of inflection. It does not have to have that many points of inflection, but it cannot have more. So a quadratic and a linear, neither of those are capable of having points of inflection by this big idea. And that is it for today. So if you have any questions, please make sure that you ask. Otherwise, I'll see you in the next one.